We're now going to talk about alternative definitions of the differential operators. So first remember that using Cartesian coordinates, we can write the gradient of a scalar field, gradient phi, using the del operator, ei hat del del xi. This is equal to the partial derivative of phi with respect to x ex hat, and then plus partial derivative of phi with respect to y ey hat, plus partial derivative of phi, our scalar field, with respect to z ez hat. Okay. Now the divergence operator, if I take the dot product of the vector with this operator, I obtain del ax del x plus del ay del y plus del az del z. Because, for example, for the first term here, this is ex hat del del x. Dot product with vector a gives me the x component of vector a, and taking derivative with respect to x. And curl of a is basically, remember, this determinant. We have ex hat, ey hat, ez hat, or e1, e2, e3, and then we have del del x, del del y, del del z, and then we have ax, ay, az. And we take this determinant with respect to first row, for example, using plus, minus, plus. Here, we're going to obtain terms like del ay del x minus del ax del y in ex hat direction. And then we have, for example, minus, for the second column here, del az del x minus del del z of ax. This is an ey hat direction, and this continues with the ez hat term. Okay, now it turns out that there is also an alternative way of defining these differential operators, and we will prove these in the exercises. That's using the integral definitions. The gradient of a scalar field phi can be defined as limit as s and v go to 0, where S is the closed surface area that surrounds a volume V, which is including the point of interest. So we have a point here, and we have a volume that surrounds it, and that includes this point, and the volume is basically bounded by these surfaces. Okay, so for each definition, we have the limit as s and v go to 0, which means the differential limit. And at the denominator, we have the integral over the volume d tau, which is our differential volume. And for the gradient operator, we have the closed surface integral phi, our scalar field, d sigma, the differential area. For the divergence, we have the divergence of the vector v is d sigma dot product with the vector v. And for the curl, we have d sigma cross product with the vector v. All right, so you can see here we have gradient, divergence, and the curl. So for example, if you consider this right surface here, this d sigma vector will be pointing to the right. So I'm defining the d sigma vector in the outward direction of this volume, which is parallel to the normal vector of this surface, of each surface. And for each of these surfaces, I have to perform this integral and add them up to get the closed surface integral phi d sigma. And then I have to divide it by the integral over the volume d tau. So this could be dx dy dz, and this is, for example, dx dy. Then you will have 1 over dz here, which means we're taking the derivative of phi with respect to z, and d sigma vector would be dx dy in ez hat direction. So you can see how that would work. And here I have, for example, dx dy in ez hat direction, dot product with the vector v gives me the z component of vector v divided by dx dy dz. Dx dy's would cancel. That means del vz del z, for example. So you can see how that would correspond to divergence. And here I have a similar situation. So this, for example, could be dx dy ez hat cross product with vector v divided by dx dy dz. And so that would give me basically the term that's going to be ez hat cross with vector v, so that's going to be in that direction, and dx dy divided by dx dy dz would give me d dz, so that would give me a term that would have del z, for example. Okay, so that's how I see the correspondence between this and this, but we're going to have formal proofs of these integral definitions in the exercises. Okay, so once again, in Cartesian coordinates, gradient of a scalar field phi is the derivative, partial derivative with respect to x ex hat plus partial derivative with respect to y ey hat plus partial derivative with respect to z ez hat. The divergence, x component partial derivative with respect to x plus y component partial derivative with respect to y plus z component partial derivative with respect to z. And the curl is calculated using this determinant ex, where the first row is ex hat, ey hat, ez hat. The second row corresponds to the del operator components, del x, del y, del z, and the third row corresponds to the components of vector a, ax, ay, and az. And this, if we open this up, use according to the first row here, plus, minus, plus. First row, first term, we have del az, del y, minus del ay, del az, del y, minus del z of ay. So this doesn't look right. Let's correct it. So we cross out the first row and first column, so del az, del y. Minus del z, del ay, del z in ex hat direction. As for the second term, we cross out the first row and second column, del az, del x minus del ax, del z. So that's with a minus sign here, minus ey hat direction. So, and so on and so forth. For the last term, we would have del ay, del x minus del ax, del y in easy hat direction. So that would be the third term here.